Hi there. In section 2.6, we are going to talk about something called higher order derivatives. So since the derivative is a function, then the derivative is something that we can find a derivative of. And then we can find the derivative of that, and then we can find the derivative of that, and we can actually keep on going as many times as we want. So higher order derivatives means taking derivatives of derivatives. That's it. So the order is the number of times that we differentiate a function from what we'll call like the original function, or like where we started. So there are a few different ways of notating derivatives. We have been finding first derivatives since we've been starting to take derivatives. But there are second, third, fourth, fifth, sixth, hundredth, thousandth if you want. And yeah, we will see an application of these. Beyond the third derivative, there isn't really much of an intuitive meaning to these. So I don't know if you like that or not, but anyway, so the notation for derivatives, we've got a few different ways that we can notate them, because we have a few different ways to even notate the first derivative. So here's just a kind of chart of different ways that we can talk about the first, second, third, fourth, and in general, the nth derivative of a function. So we're starting with something that looks like f of x, or we could say y, if that's the way that our function is given to us at first. So the first derivative, as we know, can be notated as f prime of x. It can also be notated as y prime. It could also be notated as dy dx. And it can also be notated as d dx, the derivative of f of x. The second derivative is notated the same way, except we just put another prime. We put another apostrophe thing. So the second derivative, we'd say f prime prime, or f double prime, or just the second derivative of f of x. Same thing for y notation. So we would write y prime prime or y double prime. The dy dx notation gets a little bit different. We write d, and then kind of looks like a square on the d, y, and then dx, and then a square. So that means we found the derivative twice of y, and we did it twice with respect to x. So that's why the square is on the x in the bottom and the square is on the d in the top. This would be the derivative of the first derivative. So the derivative of f prime of x, or d dx of f prime of x. Sorry, my iPad cut out for a sec. So d dx of f prime of x is our last way to notate this. That just means the derivative of the first derivative. And that's what a second derivative is. The third derivative would be finding the derivative of the second derivative. And the way that we notate that would be f prime 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 of x, or f triple prime of x. We can also notate it as y prime prime prime, or y triple prime. The dy dx notation gets a similarly, weird kind of thing. We do d and then kind of cubed of y over dx cubed. Nothing's being cubed though. It just means that we are differentiating the original function 3 times. And then of course this would be the derivative of the second derivative. So the derivative of f double prime of x. I'm gonna move this up a little bit. Okay. The fourth derivative, here's where we kind of stop putting primes because it gets really crowded up there and it's hard to distinguish them and count them. So from the fourth derivative and on, we're going to put a 4 here between the f and the parenthesis. But this is reserved, this means exponents. So when we want to talk about the derivative, the fourth derivative, we put a parenthesis around the number. Okay, same thing for the y notation. Not y to the fourth, but this would mean fourth derivative of y. The dy dx notation stays the same. So this would just be d kind of to the fourth, but it just means differentiating 4 times, and then dx to the fourth, but not really to the fourth. It's just meaning we differentiated where x was our variable 4 times. And then, of course, this is the derivative of the third derivative of f triple prime of x. So just more generally, skipping ahead to the nth derivative, this would be represented as f parentheses n in the exponent, but not really exponent. This would mean the nth derivative, past 4. As we do y, again, parentheses n in the exponent place, we would just have d to the n, but not really to the, just as a, in that place, superscript place. And then this would be the derivative of the n, the previous derivative, so the n minus 1 derivative. Okay, so we aren't going to really need to use this too much. We want to be familiar more with these ways of notating, but just in case you see this in the future, it does mean the same thing. So let us find the fifth derivative of the function 2x to the fourth minus 5x cubed plus 21. So this is the original function. Now, in order to get to the fifth derivative, we have to differentiate the fourth derivative. In order to get there, we have to differentiate the third derivative. In order to get there, we have to differentiate the second. In order to get there, we have to differentiate the first. And in order to get there, we have to find the derivative of this function. Well, what I'm trying to say is that we have to go through all of the derivatives, right? And then this just tells us that we stop when we get to the fifth one. So we'll find f prime of x first. Okay, so that'll be 8x cubed minus 10x squared plus 0. All right, so there's f prime of x. F double prime of x, or the second derivative. This will be 24x squared minus 20x to the first. All right, f triple prime, the derivative of the second derivative. In other words, the third derivative. We're differentiating now the second derivative, so we'll bring the 2 down and multiply. That'll be 48x to the first minus the derivative of 20x, which is 20. Okay, the fourth derivative, here's where our notation switches. We're going to find the derivative of the third derivative. So it'll be 48 minus 0. And then lastly, our fifth derivative will be the derivative of 48, and that's just 0. All that work for 0. So notice it as you differentiate simple polynomials, the derivatives get simpler and simpler because they're losing a degree every time. So every derivative thereafter the fifth and on is going to be just 0. And that's true at some point for any polynomial, depending on what the degree is. Right here we started with 4. So at some point we will get down to a degree of 0, and then it'll just stay at 0 that whole time. Okay, let us find the third derivative of f of x equals 2x plus 2 over 1 minus 3x squared. So we should start by finding the first derivative. Now, if you look at what the function consists of, we have a 2x, then we have plus this other part, 2 over 1 minus 3x whole thing squared. Now this part here is a quotient, so we have to be careful when we differentiate it. We could use the quotient rule, but it is a quotient of a certain format, one that we just talked about, where the number up top is, or the thing in the numerator is a number up top, right? There's no variable stuff up there, but there is variable stuff in the bottom. So when that's the case, I highly encourage you to rewrite this in a way that doesn't have a quotient. So the way to do that would be to bring up that denominator and multiply the 2 by 1 minus 3x to the negative 2 power. There's a negative 2 there. It's just not popping up right now. Hello, iPad. Are you awake? Well, it'll come in a second. So now what we can do is we can use the chain rule instead of the quotient rule. Okay, so to find the first derivative, we will differentiate 2x. That gives us 2. Then we will differentiate 2 times 1 minus 3x to the negative 2 power. Okay, so we're going to bring the negative 2 down and multiply by the positive 2 here. So that'll give us minus 4. And then we leave the base the same, and we subtract 1 from the exponent. So that'll make us have an exponent of negative 3. Then, this is only half of it, right? With the chain rule, we have to multiply by the derivative of the base, or the derivative of the inside function. So the derivative of 1 minus 3x is negative 3. So you have to take the time to write out b and b prime. That's totally fine. Pause this and go ahead and do that. Make sure you know where this is coming from. Right, this whole thing here is with the negative 2 is the derivative of that part there using the general power rule or the chain rule. Now before we go ahead and find a second derivative, it's a good idea to simplify. Meaning this negative 4 and this negative 3, we should probably multiply those, but this 2 is separate. So we'll get 2 and then plus 12 times 1 minus 3x to the negative 3. And here I want to leave that as negative 3 exponent because I'm going to want to differentiate this again. So the second derivative will be found by finding the derivative of the first derivative. I've said derivative so many times in this video already. So let's see, we've got the derivative of 2, that is 0. All right, then here, when we differentiate that, we can use the chain rule again, or the general power rule. So the negative 3 is going to come down and multiply by the 12. All right, so that's negative 36. We've got times 1 minus 3x, and we'll lose a degree, so we'll become more negative, negative 4. Then again, we have to multiply by the derivative of the inside, which is still negative 3. Now we'll simplify this by just multiplying the negative 36 and the negative 3 together. And let's see what that comes out to be. 3 times 36 is 108. All right, we're almost there. We just have to differentiate this one more time to find the third derivative. So it'll be f prime prime prime, or f triple prime. So we will take this negative 4, again, just another general power rule, bring this negative 4 down and multiply. 108 times negative 4 is 432, negative 432. We leave the base alone. We subtract 1 from the power. And then again, we have to multiply by the derivative of the inside, which is still negative 3. Okay, negative 432 times negative 3 is 1296. We've got 1296 times 1 minus 3x to the negative 5th power. And here is a good time to convert back to a fraction because we are done differentiating. So the 1296 will stay up in the numerator. Instead of being multiplied by the 1 minus 3x, it's going to be divided by the 1 minus 3x. We just have to change the power to a positive 5. And there we go. There is f triple prime for that function that we started with. Okay, in our last example here, we've got already, we know the third derivative. We are given that y triple prime is the square root of 2x. And we want to find the fifth derivative of 4. Okay, so our answer here, the fifth derivative of 4, that's going to be a number. It's going to be the fifth derivative, evaluate it, we're going to need to find it with x's. Then we're going to plug in 4 into that fifth derivative, and that will give us the thing that we're looking for. Here, though, we don't have to start all the way at the original function. We're almost like halfway there, a little more than halfway there, because we already know the third derivative. So that's really nice. Okay, so if we differentiate the third derivative, we're going to get the fourth derivative. And then if we differentiate that, we will get the fifth derivative. So there are a few ways that you can go about finding the derivative of this. And here is one of them. So I would say we've got two options. So we can look at y triple prime as square root of 2x, which means that we want to write this as 2x raised to the 1/2 power. If we look at it that way, we will use the chain rule to differentiate this. Let's go ahead and actually do that. So here's option number 1. Here is option number 1. So we'll look at this as some stuff raised to the 1/2, where the base here is 2x. So we'll bring the 1/2 down and multiply. All right, so we're finding the fourth derivative. We'll bring the 1/2 down and multiply. The 2x, the inside stays the same. We'll subtract 1 from the power to get negative 1/2. Then we have to multiply by the derivative of the inside, the derivative of 2x, and that's 2. Now to simplify this, the 1/2 and the 2 here will just multiply to 1. So this is actually just 2x to the negative 1/2. Then if we find the fifth derivative, by differentiating that, we still have to use the chain rule. We will bring the negative 1/2 down in the front and multiply. So we'll get negative 1/2. We'll leave the base the same, subtract 1 from the power. Negative 1/2 minus 1 is negative 3/2. Then we still have to multiply by the derivative of the inside, which will be 2. Now again, the 1/2 and the 2 are going to divide this time to negative 1. So we have negative 2x to the negative 3/2. Now if we substitute in a 2 into this, I don't know, you could just do this in your calculator. Wait, what did I say 2? I mean a 4. There's just so many 2's in this example. You could just do that in your calculator and it'll probably give you a decimal. So we want an exact value. So I would suggest that you rewrite this before we go substituting in as maybe, well, negative 1 over, what do we have here? The square root of 2x to the third. Oh, hello iPad, come on, you can do it. Oh, it's trying so hard. Okay, there we go. So now we want to substitute in 4. Okay, so that's going to be y with derivative of 4. So that's negative 1 over the square root of 2 times 4 cubed. 2 times 4 is 8, and then 8 cubed. I don't know what 8 cubed is. Let us see. That is 512. Now I'm sure that there is a perfect square that you could pull out of this. Yes, absolutely right. It's divisible by 64 because we just did 8 times 8 times 8 in there. So we could look at this as 512 is 64 times 8, and then that 64 can come out. Oh, we can even must be able to do another number in here that's perfect square too, because 8 will have a perfect square inside it as well. So I don't know, let's see what this, so So we'll have negative 1 over 8 square root of 8. 8 under the square root is 4 times 2. So one of those 4's can come out as a 2, multiply by that 8, so it'll be 16 radical 2. Ugh, negative 1 over 16 root 2. Let's just, for sake of understanding what that number is close to, let's just get a decimal approximation of this. So that's about negative 0.044. Wait, 0.044, so 0.044. Okay, so that's one way. I'm just gonna make this a little bit moved over so that we can have some space for the other option. Poor board work management here. Hang on a sec. Move that up and bring this guy down here. Okay. So the other way that you could view this or think about this, the other option, is you could avoid using the chain rule altogether. You could say, all right, I'm going to look at y triple prime, which is the square root of 2x. I'm going to look at that as square root of 2 times square root of x. And that's the square root of 2 times x to the 1/2. Okay, so now when you find the derivative of this, that radical 2 is a constant multiple. So that will multiply by the derivative of x to the 1/2. And that'll be 1/2 x to the negative 1/2. So another way to write that would be radical 2 over 2 times x to the negative 1/2. When we find the fifth derivative, we still have a constant multiple, this radical 2 over 2, multiplied by x to a power. So this is just simple differentiational stuff. So that root 2 over 2 will stay. We'll multiply by negative 1/2 x to the negative 3/2. So that'll be negative radical 2 over 4 x to the negative 3 over 2. Now another way to write this without a negative power would be negative radical 2 over 4x to the 3/2. And then we want to convert that into a root. So that'll look like 4 square root of x cubed. Now I guess what we could do even is take out an x, look at this as x squared times x and take out an x. I don't know, this isn't like too important. It's more finding the derivatives, like, the higher order derivatives. But in any case, then you can still plug in 4 into this, and you will get some value that will look different than our answer here, which is negative 1 over 16 radical 2. But it will be equivalent. It'll just be like rationalized in a different way. You'll probably get negative root 2 over 32, I think would be the answer. Okay. So in the next video, which is our last video for this week, we will look at the higher order derivatives in the context of a real life situation, which a typical application to this stuff is to physics.